We'll get started with our first press conference, which is about early results from the Mars Atmosphere and Volatile Evolution mission, which is MAVEN. Our speakers, in the order in which they'll speak, are Bruce Jakosky. He's the MAVEN principal investigator with the Laboratory for Atmospheric and Space Physics at the University of Colorado Boulder. Jasper Helekas, SWIA instrument lead, University of Iowa City. I apologize if I'm butchering anybody's names. Paul Mahaffey, he's NGIMS instrument lead with NASA's Goddard Space Flight Center in Greenbelt, Maryland. And Jim McFadden, who's the static instrument lead with the University of California at Berkeley.
Thank you. It's a real pleasure to be here today. What I want to do is to briefly provide context and then let the three scientists to my right talk about the results. At the end, I'll come back and give you an update on the status of MAVEN. MAVEN started the primary science mission about a month ago. The goal is to understand the role of loss of the atmosphere, loss of gas from the atmosphere to space through time by looking at the processes that are going on today. We're trying to understand the energy inputs into the upper atmosphere from the sun and the solar wind, the response of the upper atmosphere directly to that, and then the processes that lead from there to escape. In the end, we're going to put together a complete chain from energy input all the way through to escape. We aren't there yet. We're very early in the mission. But what we are able to do is to start piecing together some of the links in that chain. So what we're going to see today are some of the early results on the energy input, the response of the upper atmosphere, and the processes leading to escape. So with that introduction, I will just turn it right over to Jasper.
Thanks, Bruce. So I'm going to be telling you about a new population of ions that MAVEN has discovered at low altitudes above Mars and how we can use those ions to remotely monitor the solar wind from deep inside Mars's magnetosphere. So as you just heard from Bruce, in order to accomplish the MAVEN science, we need to measure the energy inputs to the system, all of the drivers coming from the sun. We need to measure the reservoir of particles in the ionosphere and the atmosphere of Mars. And we need to measure the escaping particles. And we need to do all of these as close to simultaneously as we can because we want to find out how the escape depends on the drivers. So when we put together the MAVEN mission design, we came up with an orbit that would allow us to sample all of these different things. And that's what you see in this graphic here on the screen. This is close to the current phase of the MAVEN mission, and you see that the orbit samples all of these regions. It samples the reservoirs, it samples the escape, and it samples the drivers. Now some drivers are rather easy to sample. You can see sunlight from pretty much anywhere. The solar wind is a little bit harder because it's decelerated and deflected around Mars by its interaction with the upper atmosphere and ionosphere. So you have to go to quite high altitude to see the solar wind, or so we thought. This is the current phase of the MAVEN mission. Unfortunately, the orbit precesses around, and there are portions of the mission where we won't directly sample the solar wind. And furthermore, it's difficult to address variability on timescales faster than the orbit because, of course, MAVEN can't be in two places at once. But we may have gotten really lucky here. There we go. So this is a typical solar wind spectrum measured by the SWIA instrument. This is the bread and butter measurement of the instrument. It shows that it's working very well indeed. This is what we see at high altitudes far from Mars, outside of the Martian magnetosphere. The two highest peaks that you see there are the solar wind. Those are ionized hydrogen and helium streaming out from the sun at supersonic speeds. In fact, they're traveling about 350 kilometers per second, which is a large fraction of a million miles an hour. So this is what we expect to see at high altitudes, and this tells us a lot about the solar wind. It tells us the density, the velocity, the temperature, all of which we think are important in determining the loss of atmospheric gases from Mars. There's a third peak on that spectrum, which you see at the far right, which is actually newly born hydrogen ions formed from the outermost reaches of the atmosphere of Mars. This is what we see when we go down to much lower altitudes, down into the ionosphere. All of this stuff at high energies goes away, and you only see low energy ions. This, again, is what we expected to see. Those low energy ions on the left of the spectrum are the ionosphere of Mars. There are some very interesting things going on there, as you'll hear later from Jim and from Paul. But this is still what we expected to see. Now here's what we did not expect to see. When you go down to still lower altitudes, lower than any previous spacecraft with comparable instrumentation has gone, suddenly there's another peak at high energy that pops back up. So this is kind of remarkable. There's a population at the solar wind energy that's there at high altitudes, goes away at middle altitudes, and comes back at lower altitudes. And it's not just close to the solar wind, it's dead on the solar wind. You can track this day after day, orbit after orbit. Every time we go to low altitude, down to this region below about 200 kilometers, we see this population popping up and it tracks the solar wind. So this is a neat trick. How is this happening? Here's what we think is happening. What we believe is happening is that with some small probability, solar wind protons streaming in from the left can interact with the outermost reaches of the atmosphere of Mars, and they can change color like a chameleon. They pick up a charge and become neutral. That reaction, by the way, is the same reaction that produces that third peak that I showed you in the spectrum, the newly born hydrogen ions. But what it does is once these particles become neutral, they can completely ignore all the interaction with Mars's magnetosphere, and they can penetrate what we thought was an impenetrable barrier, dive down to very, very low altitudes. Once they get down to low altitudes, though, they interact with the dense ionosphere and atmosphere that's there, and they can change color back to the form in which we can measure them. In other words, they can become charged again, we can see them. So we're still exploring the implications of this population for the upper atmosphere of Mars, but one thing that we know for sure is that it allows us to measure what the solar wind is doing while we're deeply immersed in the Martian magnetosphere. So we can instantaneously see what the response of the ionosphere and the escaping particles is to what's going on in the solar wind and what the driving energy is. So now I'm going to turn it over to Paul, who's going to tell you more about some of the other things going on in this region.
Great, thank you, Jasper. So we're discovering really remarkable structure and variability in a whole suite of atoms and molecules and charged particles in a region of space that's really being explored in detail for the very first time with the MAVEN mission. And this region is, we just call the upper atmosphere of Mars, as distinct from the lower atmosphere of Mars. And I'm trying to show in a cartoon here, as clearly as I can show in a picture, how you represent a very thin atmosphere. In the lower atmosphere, the atmosphere that's near the surface, it's much less dense than the Earth's atmosphere, about mostly CO2, about 1% the pressure of the Earth's atmosphere, less than 2% of argon and nitrogen, even less oxygen and other trace species, carbon monoxide and so on. But there's all sorts of processes happening in this region of the atmosphere that propagate up and influence the upper atmosphere. For example, on the right, I'm trying to illustrate some dust storms, and as dust storms often happen on Mars, they heat up the atmosphere, they raise the atmosphere. As the atmosphere flows over topography like big mountains and so on, you create waves in the atmosphere, and these waves can propagate upward as well. The upper atmosphere is really different. The upper atmosphere is that region of space that's kind of 75 to 300 miles from the surface. It's very thin, it's very tenuous. It's so thin, in fact, that heavy and light molecules can diffusively separate from each other. The light ones make their way higher in the atmosphere compared to the heavy ones. And when you get inputs such as solar ultraviolet radiation and it photodissociates, it breaks apart carbon dioxide or it creates ions, then some of those ions and atoms just stay up there. They don't instantly react like they do in the lower atmosphere. And so in the upper atmosphere, you have both a population of atoms, of molecules, and of charged particles. We're studying the electrons in that region with another instrument. But what I'm going to talk about today in a little bit more detail is what we're learning with an instrument that we developed at NASA Goddard called NGIMS, a neutral gas and ion mass spectrometer. And what I'm showing here is two spectra. We call these mass spectra, where we're basically sorting out the different molecules or atoms by their mass channels, showing the mass channels here from about 2 to 60. And this spectra was an average taken at about 200 kilometers, 125 miles or so. And on the top, we have the mass spectra of neutral atoms and molecules. And we have, the point to be made is that we have both molecules and atomic species in this region. On a previous orbit, we had obtained a very similar spectra, that's on the bottom, but this time of ions. And so you can see that spectra, we sort out all these atoms and molecules by mass with unit mass resolution, basically. But to understand what's going on as we kind of dip down every orbit into this region of space with MAVEN to study both this region and the input from the sun and the region above this upper atmosphere region. Take a look at this graph. Where on the right I've plotted altitude in the green, this time in kilometers. You can see that we're dipping down to just below 200 kilometers. And we transit through this region very quickly. The scale there is from minus 600 to plus 600 seconds. So we dip in and out of the atmosphere. And what you can see on a log scale, because the dynamic range of densities, the difference in densities is so large, I've mapped a number of species here, the most abundant being carbon dioxide, as you might expect. But then I show atomic oxygen. You don't find this in the lower atmosphere. You only find it in the upper atmosphere. And so we have these atomic species, noble gases, nitrogen. The nitrogen and the oxygen can combine to form NO. And what's really interesting, which doesn't show up as well in this log plot as it would be on a linear plot, is this structure in the peaks. You see these little wiggles in the peaks. Those are real. That's real structure, and that structure changes from orbit to orbit. And so we're really studying this region in a lot more detail than we ever have below, because we're dipping into it and making measurements every orbit. And what you see on the next slide is just a similar plot, but this time it's for ions, charged particles in the atmosphere. You can see that the most abundant ion is not CO2, as you might guess, because that's the most abundant gas in the lower atmosphere, but molecular oxygen. And it's kind of fighting for prominence with atomic oxygen, way up at about, looks like above 250 kilometers or so coming in. Atomic oxygen just edges out molecular oxygen, but then you go through a peak in the atomic oxygen density, and it kind of dips down as you go to lower and lower altitudes. So we're mapping these out as we essentially precess around Mars. We're in the day side of Mars now. We'll be precessing into the nighttime. We'll be covering all sorts of latitudes. We'll be looking for seasonal changes and so on, and particularly looking for how this region of the atmosphere changes with inputs from below and inputs from above. So it's important to study this region of the atmosphere because it really is the reservoir. It's the source of gas that forms the atoms that escape forever from Mars. And that's really the point of the whole mission, to kind of understand the history of escape from Mars, understand how loss of the atmosphere over billions of years might have changed the ability of the surface of Mars to sustain life. And so we're just beginning on that exploration, and look for lots more results coming from all the investigations of MAVEN. And with that, turn it over to Jim.
Thanks, Paul. My experiment is called STATIC, which stands for superthermal and thermal ion composition, and it makes a measurement very similar to Paul's experiment. Its primary objective is to measure the entire acceleration process at Mars, and it's really the first experiment to do this, to measure the entire process from very cold ionospheric ions, like Paul's experiment can also measure, the heating of those ions to escape velocities, which is needed to understand the loss processes, and also the eventual acceleration of very, very high energies as these ions move away from the planet. The sensor is shown here on the right. It actually hangs off the bottom of the spacecraft on a platform that allows it to be pointed in the direction to make the best measurements. The upper portion of the sensor is an ion analyzer that measures the energy and direction the particles going. It's followed by a velocity analyzer that allows us to be able to determine the mass. The velocity analyzer actually uses a 15,000 volt supply to accelerate the ions so they punch through a couple of very thin carbon foils. They're only about 10 to 20 atoms thick. And when they do that, they kick off electrons, and we measure the time difference between those electron signals to less than a billionth of a second. And by doing that, we can determine the mass of the ions. This is an example of the kind of composition spectra, the mass spectra that we get. Mass is plotted along the x-axis. I've labeled the different peaks, much like you saw in the earlier plots by Paul. Hydrogen, you see alphas, He+, and hydrogen molecules. Oxygen atoms, O+, oxygen molecules, O2+. There's a shoulder of CO2+, which we can use modeling to pull out of the signal. And this is the basic measurement in one of the dimensions, but static actually measures in 3 different. It measures the direction and it measures also energy. So generally we display these showing 2 of those dimensions as shown here, where we plotted energy along the bottom axis and mass along the y-axis. As we look at this, we can see there's one primary peak where there's O2+, oxygen molecules, and that's the dominant species at this low altitude. This is about 250 kilometers. The width of that, the energy that you see the O2 peak at, is actually determined by the spacecraft motion. The spacecraft's moving very, very fast, and so that determines the ion energy. The width of that peak, in energy, left to right, actually is determined by the temperature of the ions. These ions are less than minus 100 degrees Celsius. They're very, very cold. As we go up in altitude, we see a composition change, and we see the O2+ peak decrease, and the O+ peak become about equal to the O2+ peak. So we see a change, and we also see the protons, the hydrogen peak, lower in the plot, also appear. And this composition change happens relatively quickly from about 250 to 300 kilometers. Again, these ions are still very, very cold. They still don't have escape velocity, but we move a little bit higher in altitude, and here it shows at 400, and we see those peaks spreading in energy to the right, which gives them where they're accelerated enough to have escape velocity to be able to leave the planet. As we go even higher in altitude, we see them accelerated to even higher energies as they move to the right, where they really start to energize. And at this point, they have about 10,000 times the energy that they initially had. Eventually, these ions are accelerated, and they'll have more than 1,000,000 times that energy, at least for the heavier ions. So they really get very, very high energy compared to the very initial cold population. We can summarize this whole thing in kind of a cartoon here, so you can kind of see where all this takes place. Here I've drawn in a little circle around where those measurements were taken. And what we see is at very, very low altitudes, again, we see a very, very cold population. As we move up, those ions heat, they get energized to escape velocities, and eventually get accelerated away, forming a plume that's kind of shown in blue over the pole. Those plume ions, almost like a mohawk off the planet, will be accelerated up to more than 1,000,000 times the initial energy of these particles. And with static, we can measure not only from the very lowest energy ions all the way up to these high energy ions. And this is a really important process because this is one of the main processes for atmospheric loss that is the main mission objective for MAVEN. I'll turn it back to Bruce.
Thanks, Jim. I have a couple of closing comments. The first is, again, to provide the context. What we've tried to do here with the mission is to measure from the energy input to the response of the upper atmosphere to the escaping ions and atoms. We don't have that complete chain filled in. We're just starting the mission. It's going to take us a few months to get the data and understand how the instruments are working. But we've picked 3 different aspects of that to show today, each one of which represents a significant discovery of what's going on in the upper atmosphere and in the interactions with the solar wind. The second comment I want to make is on the status of MAVEN. Like I said, we've been in orbit since September. We completed commissioning of the spacecraft in mid-November, and that's about a month ago. That means we're about a month into our year-long primary mission. The spacecraft and all the instruments are working as expected. And to me, that's the most exciting part of this today, the fact that we are there with full technical capability as intended when we set out with this mission. That means that we're on track to be able to get the observations we wanted. It's especially important to me that we were able to do this on schedule, to launch when we set out to, and to come in significantly under the budget we were approved at 5 years ago. So with that, I will close, and Peter, I'll turn it back to you for Q&A.
Thank you. Okay, so just to repeat a couple things. We welcome questions from reporters. If you're not a reporter, please refrain from asking questions. And when you do ask questions, please state your name and your affiliation.
Thanks, Peter. Alex Witzy with Nature. This is for anyone who wants to take it, maybe Bruce. I just wondered if you could talk a little bit about solar variability and whether you've seen any responses to any changes in the solar wind storms or anything in the last month.
I'm actually going to let Jasper answer this because he's looking at the effects of solar storms more than I am right now.
Yeah, so it's actually been a very interesting time period to be at Mars because the solar wind has been pretty variable while we've been there. We haven't seen the storm of the century yet, but we've seen some high-speed flows. We've seen some CMEs, not big ones, but the solar wind has been very variable while we've been there. And we're still exploring exactly what the atmosphere is doing in response to that. I don't think I can completely answer that question yet because there's work to be done. But we're starting to fill out the parameter space and see how the system responds to a pretty good range of solar wind drivers.
Rick Lovett, freelance. I may have missed this, but when you see these protons changing color, as you called it, why doesn't that happen in the Earth's magnetosphere also? Because why was that a surprise?
So I was sitting in my hotel room last night actually thinking about exactly this question, and I'm not sure I have an answer. I'm sort of curious to go back and look and see if you could see traces of a similar process at the Earth's magnetosphere. One possible answer is that the relative scale sizes of things are very different in terms of how far out the atmosphere extends compared to the size of the magnetosphere. So I expect that that's part of the difference, but I don't have a full answer for you yet.
Hi, yeah, Eric Ham with Science Magazine. Alex asked about kind of seeing solar storms, looking for the storm of the century. I wonder if you could say something about kind of almost an artificial storm of the century when Comet Siding Spring crashed. You were hoping that you could use this as a sort of artificial input of energy. Maybe one of you can tell us what you saw and what you've been learning from that encounter.
Let me take a start, and then if any of these other guys want to pipe in. The comet passed by on October 19th, closest approach. We were in hunker down mode, what we called hunker down mode, in order to ensure the safety of the spacecraft and instruments, but we turned on as quickly as possible after it became safe to do that so we could try to see the atmosphere as soon after as possible. The biggest effects we saw immediately were the presence of metal ions in the upper atmosphere that indicated that dust from the comet had in fact made it to the planet and hit the planet and vaporized and ionized. We were seeing that for up to several days after the encounter. The artificial experiment aspect was complicated by the fact that CME from the sun hit Mars just a couple of days before the comet closest approach. If we had our druthers, these things would be nicely spaced out. They all happen at once, which means we have to try to separate out the different effects. That's going to require getting some experience now with the Mars upper atmosphere without the comet and looking at the data in detail over the subsequent several months, and then we'll be able to go back and look and really pick out what's happening from the comet versus the CME. Again, Jasper, do you want to comment on that? I know you've looked at it.
I think you said it very well. There were a lot of things happening at the same time that made it difficult to deconvolve things. We certainly saw effects of the comet. There have been results reported from the UV spectrometer and from Paul's instrument, which maybe he wants to comment on. But having the CME there at the same time made it tricky to understand what was going on.
Yeah, with the mass spectrometer, we were doing kind of full mass scans down around the 200-kilometer range, just a little bit before. And we were having our Thursday science telecon, and the IUVS guys said they saw magnesium, I guess it was. And so we went running off to look at our spectra, and right away saw a number of of metal ions in that region, iron and chromium and zinc and potassium and sodium and so on. So that was pretty exciting. What we're looking at carefully now is, did all that energy that went into the upper atmosphere really change it in any way? Did it heat it up, for example? And looking particularly at the density of a couple of robust signatures like argon and carbon dioxide, it sure looks like it did. But we're very early in that process, and we want to explore that data a little bit more. But it certainly looks from our data like there were effects of just all that energy going into the atmosphere in addition to these interesting metal ions that came in from space.
I have a question from Camille Carlisle of Sky and Telescope that she's asking via the web. The question is for Paul Mahaffey. What does the structure in the spectra mean? For example, are there pockets of increased concentration of certain atoms and such?
Yeah, absolutely. These are really density variations, pressure variations, and the atmosphere is the atmosphere is very well modeled with general circulation models and so on, but they typically don't have the resolution to really get down to that very fine scale and look at dynamics, and so they really need a basis of experiment to go back and feed those into the models. And so what we're seeing perhaps are waves that are created in the lower atmosphere, and they kind of propagate up and they break in the upper atmosphere. And that's where we're seeing density variations that are propagating up from the lower atmosphere. To study this carefully, we'll need really to look at it at all times of day. We'll need to see whether that's being convolved with energy inputs coming in from the sun and so on. But it's real density variations and just a remarkable structure. These are changing by tens of %. You couldn't see that too well in the log plot, but really large changes in density in all the species that we're measuring.
If you have another from the chat, you can go ahead.
I do have another from the chat. This is a question from Irene Klotz at the Discovery Channel News and Reuters. The question is for Paul and or Bruce. I realize the MAVEN mission is all about putting together the small pieces of the puzzle to understand Mars' lost atmosphere. But in light of the paper last week providing strong evidence of surface water at Gale Crater for perhaps tens of millions of years, do you have any inkling yet on what's missing from the computer models to account for a thick atmosphere for that length of time?
Let me take a start at that, and then Paul. The evidence from Gale Crater, from Opportunity, from the orbiter imaging is pretty compelling that there's been liquid water on the surface in the past, and the driver must have been greenhouse warming from the atmosphere that would raise the temperature, allow liquid water to be more stable than it currently is. The question is, how do you account for the change in climate from that early atmosphere to the present day atmosphere? The CO2, the water that you see evidence for on early Mars can go down into the crust and get locked up, but we don't see evidence of the thick reservoirs, thick deposits of carbon-bearing minerals that you would expect to see if all the CO2 went down. MAVEN is about looking at whether the gas could have gone up to the top of the atmosphere and been lost to space that way. We're piecing together a very complex puzzle of where did the early atmosphere go, where did the greenhouse atmosphere go, and by looking at the surface, which the rovers have been doing and which the orbiters have been doing with imaging and spectroscopic analyses, by looking at the upper atmosphere, which MAVEN is doing, we can get an understanding of what processes have operated. Paul, do you want to add on?
Yeah, let me just add a little. One signature of the atmosphere being lost to space is tied up in the ratio of heavy to light elements in the atmosphere and isotopes. And for example, one robust signature that we can measure with MAVEN, but we got a really good head start on with our Curiosity investigation on SAM, is, for example, the ratio of these primordial argon isotopes, argon-36 to argon-38. And that's really showing that over time, the lighter isotope has escaped faster than the heavier isotope, as you'd expect. And argon is not confused with anything that might be going back into the surface. For example, if carbon dioxide went back into a very early ocean and formed carbonates, we've not seen the cliffs of Dover yet on Mars, but if it did, then the fractionation would go in a different direction from lost to space. So we made a good head start on understanding some of these signatures, but in order to understand the current escape processes and how they vary with solar input, we really need the data from the MAVEN mission.
Do we have any, do we have any other questions? Mary Catherine, are there any other questions from the chat? Okay, then we're done. Thank you all for being here for this press conference. Our next press conference will be at 10:30, and that's about the latest look at X-rays and gamma rays in thunderstorms.